Okay, we're back with the second video for the chain rule. So here's the deal. Chain rule allows us to derive composite functions. So real quick, composite functions, if you remember, that was your f of g of x or your g of f of x. It really didn't matter what the letters were. You could put an h in there. But this is when you plug one function into another function. So for example, if f of x was equal to the square root of x and g of x was equal to x cubed plus 1, then f of g of x would be the square root of x cubed plus 1. We literally took g and plugged it in for all the values of x that are in f. Okay, that's a composite function. Now, if I asked you to find this derivative, you'd have to turn, in other words, if I asked you to find f prime of x, you'd have to turn this into x to the 1/2, but you could do that derivative by using the power rule. And if I asked you to find this derivative right here, you'd be like, Sylvain, no problem at all, piece of cake. I can get the derivative of x cubed plus 1. What we're now looking at is the composition of the two. How do we do the derivative of the square root of x cubed plus 1? That's where the chain rule comes into play. Okay, so what do we need to do? We kind of need to isolate the two functions. We need to isolate the outside function and the inside function. Here's an example. We have the function y is equal to the quantity x squared plus 2x minus 1 cubed. Okay, now, if we look at them separately, all right, if that cube wasn't there, that wouldn't be a hard derivative at all. That'd be a piece of cake. But the cube is there. Same thing, if inside where my hand was, if that was just x, or any other letter besides x, any variable, we would have that variable cubed. Again, an easy derivative. And that's what we have to kind of look at. If I had asked you, what's the derivative of y equals x cubed, you could find that real easily. But we don't have x cubed. We have something more than x cubed. We have a function being cubed. We have something, I'm going to use the word I used in class, we have something ugly being cubed. We have, this right here is the ugly thing, and it's being cubed. And we have to get the derivative. So here's what we're going to do. We're going to identify that as ugly. So we're going to say ugly, and ugly begins with the letter, yeah, that's right, ugly begins with the letter u. So we're going to say, you know what, u are going to be equal to x squared plus 2x minus 1. The ugly thing is x squared plus 2x minus 1. Okay, that's our ugly. And if we know that, that inside function is our u, then we can redefine y. Y is actually going to be, instead of the quantity x squared plus 2x minus 1 being cubed, y is just going to be u cubed. Because by substitution, u is equal to x squared plus 2x minus 1. Okay? Now, why do we want to do this? Well, here's the deal. If I asked you to find this derivative, the derivative of y with respect to u, you could do that, right? Absolutely. We want the derivative of y with respect to u, dy du. All right, what is the derivative of u cubed? Good. You probably wrote in 3u squared, and you'd be correct. That's a nice, easy derivative. We could do the same nice, easy derivative over here, except this will be the derivative of u with respect to x. All right, because our independent variable over here is x, just as our independent variable over here was u. What would be the derivative of u with respect to x? Yeah, it would be 2x plus 2. Okay, why do we want to do that? Well, it goes back to the whole running from the previous video. We want, our goal, remember, is dy dx. Well, dy dx can be dy du times du dx. Look what I've written right here. It's the same thing as what we did before, except last video it was a's and b's and c's. We said that dA dB times dB dC was equal to dA dC. You can go back and watch that video again. Same, we got all the d's again, except now it's x's and y's. Our goal is to get dy dx. So we have dy du and du dx. So we just have to multiply these two expressions together, and we have our derivative. Let's do that. So dy du was 3u squared. Du dx was 2x plus 2. Okay? Now that's pretty good, but we still have a problem. The problem is that we want dy dx. We want our derivative to be in terms of x. And this derivative is not entirely in terms of x. We have to do a little quick back substitution. We don't want u here. Well, u is x squared plus 2x minus 1. So by substitution, we can place that back in. So we have the 3, and we have the square. But instead of u, we're going to have x squared plus 2x Plus 1 or minus 1? Minus 1. Okay? So we just replace that u with the expression which u is equal to. And of course, we still need that 2x plus 2 at the very end. Now we have our derivative. This is your chain rule right here. Okay? The key thing to remember with the chain rule is if you look at this, let's go back to this problem right here, y equals x cubed. If I asked you for that derivative, you would have said, yes, you would have said dy dx is 3x squared. Well, look at this template, 3x squared. Look at what we have down here, 3 item squared. Okay? The only difference was it was this expression, this item was being cubed as opposed to x being cubed. It's like we just did this derivative as normal. Bring the 3 out front, drop the exponent by 1. Okay? But we have this little extra thing hanging on at the end. This is the little brother or sister who wants to tag along. What is it? Well, it's the derivative of the inside. The most common mistake that students make with the chain rule is they put, for a problem like this, they'll put the 3 out front, and they'll put the square, like they correctly should, up here, just like we see here and here. They do that. But then they're so eager to derive the inside, they put the 2x plus 2 right away in the middle, and they make that the item being squared. That's not what we want. We want the original item to still be there untouched. That's a plus sign. Doesn't look like it, but there we go. Plus 2x minus 1. And then we multiply by the derivative of the inner function at the end. Or we multiply by the derivative of ugly. As we do these chain rule problems, you're going to hear me say, remember, times the derivative of ugly. Keep this as normal, and then multiply by the derivative of the ugly part.